Good day, students. Today we'll be starting with the topic, the moment of a force. Let's get started. The moment of a force. For us to be able to get the true definition of the moment of a force, let's drag the following words into the correct boxes. The moment of a force is bigger if the force is bigger and acts further away from the pivot. Another name for pivot is fulcrum. The moment of a force is greatest if it acts at 90 degrees to the object it acts on. Let's check. Correct. The quantity that tells us the turning effect about a pivot is its moment. Examples of the turning effect of a force are using a crowbar to lift a heavy paving slab and lifting a load in a wheelbarrow. Now, let's get to the example of moment of a force. The three different forces are shown. Pulling on a heavy trapdoor. Which force will have the biggest turning effect? Now, we are going to drag the following words on my right here into the following boxes to show which one of them is correct. The turning effect of a force is called torque. Turning effect of a force gives the direction of force, which is responsible for how a body rotates about its own axis. The turning effect of a force is maximum when the angle between the distance and the force is equal to 90 degrees. From the diagram above, yes, force F3, which is equal to 200 Newton, has the greatest turning effect in the trapdoor than all other forces. Let's check. Correct. Now, let's move on. How do we calculate moment? Knowing fully well that the unit of moment is the Newton meter. So, let's calculate the moment of a force attached to this diagram below. If we should look at it critically, one of the things we should note is the direction of the force and also the length that is involved. If we should look at it, the direction is like this, in this direction. So you multiply the distance with the force. So moment now becomes force times perpendicular distance. And that gives us 40 times 2. That gives us 80 Newton meters. Now, balancing of moments. Now, let's drag the following words into the correct boxes. Balancing of moment is done when an object is in equilibrium. For instance, the use of a seesaw. This is governed by the rule that the total clockwise moment is equal to the total anti-clockwise moment. Can we check? Correct. The idea that an object is balanced when clockwise and anti-clockwise moments are equal is known as the principle of moment. Okay, is it true or false? Let's take true first and check. Correct. Now, balancing of moment. How do we balance moment? We have to calculate the moment acting on the children in the diagram below and show that the total clockwise moment is equal to the total anti-clockwise moment. Now, how do we know the direction of the anti-clockwise moment? The direction of the anti-clockwise moment lies from here to here. Why? Because of the pivot. Anti-clockwise moment always lie to the left of the pivot, while clockwise moment will always lie or act on the right of the pivot. So for anti-clockwise moment, we take this direction. For clockwise moment, we take this direction. And don't forget that in this diagram, only one person is on the side of the anti-clockwise moment, while two persons are on the side of the what? Clockwise moment. Let's go for the anti-clockwise moment first. That means the distance is 2 meters, while the force involved is 500 Newton. Then I can then multiply 500 Newton by 2 meters. That gives me 1000 Newton meter. But for the clockwise moment, we have two persons. That means we have two major clockwise moments to bring together, that is to add together. For the person with 400 newtons, the clockwise moment now will now be 1 meter times 400 newtons, since he is closer to the pivot. Now, for the person far away from the pivot, he has 300 Newton, that's his force, and the total distance from his point to the pivot is 1 meter plus 1 meter, that's 2 meters, that's 300 times 2, that's 600 Newton meter. Adding 600 Newton meter to 400 Newton meter gives 1000 Newton meter. That shows that the anti-clockwise moment here balances the what? The clockwise moment. This typically shows that the what? The forces and the moments are balanced. Now, let's deal with this question. Looking at the diagram above, the beam shown above is 2 meters long and has a weight of 20 Newton and also pivoted. A force of 10 newtons acts downward at one end. What force F must be applied downwards at the other end to balance the beam? The first thing to check or see is the pivot. The pivot is that red triangle. So with that, you have your anti-clockwise moment acting in this direction, and you have your clockwise moment acting in this direction. But alas, we have 20 Newton acting on the clockwise moment side. We also have 10 Newton acting on the clockwise moment side. So we have two clockwise moments to deal with and add together. Let's take the anti-clockwise moment first. So you have 0.5 times the force. This is for the anti-clockwise moment. Now, but for the clockwise moment, we have 20 times 0.5. That's clockwise moment 1. We also have 10 times the total distance before the pivot. That will be 1.0 plus 0.5. That's 10 times 1.5. That's the clockwise moment, which is the second one. So we add the clockwise moment together. 1 plus what? 2. That gives us 20 times 0.5 That gives us 10 Newton meter. For this, the clockwise moment, the second clockwise moment, that gives 15 Newton meter. So adding 10 Newton meter to 15 Newton meter gives 25 Newton meter. So the total clockwise moment now is equal to the what? The total anti-clockwise moment. So I can have 0.5 F is equal to 25 Newton meter. F is equal to 25 divided by 0.5, and that gives me 50.0 Newton meter. Do we have 50 newtons? Oh, it's force, not moment. Force is measured in newtons. So with that, let's check and see. That's correct. Now, let's move on. Now, objects in equilibrium. Let's drag the words and see what we'll have. Then we'll check. For objects to be in equilibrium, there must be no resultant force acting on it. And the sum, total clockwise moment rather, must be equal to the total anti-clockwise moment. Can we check? We are good. Correct. Contact force is a downward force. No, contact force will always act upward. It is weight that acts downward. And the sum of the total upward forces is distance from pivot is unity. And its moment on any material is always 1. This statement is false. So let's check. Correct. Now, let's deal with this question. Calculate the unknown forces X and Y for the balanced beam shown above. So we are to drag the words into the correct boxes. Don't forget that the pivot splits the clockwise moment from the anti-clockwise moment, which acts on the what? Left. Clockwise moment acts on the right. X here denotes the force, Y denotes the contact force. To calculate the unknown force X, the principle of moment is applied. The anti-clockwise moment on the left is equal to the clockwise moment on the right. As you can see, we have X, which is the force, multiplied by the distance, which is 1 meter, is equal to 400 Newton force on the right, multiplied by 2.5 meters. So for us to be able to get X, we are going to divide the product of 400 newtons and 2.5 meters by 1 meter. That gives 1,000 Newton. The unknown force X is equal to 1,000 Newton. The unknown force Y is the what? That's our contact force, which is obtained when the weight of the pivot is determined. So the weight of the pivot is now equal to 1,000 Newton minus 400 Newton, which is 600 Newton. And the contact force Y then equals to the summation of all the forces, 1,000 Newton plus 600 Newton plus 400 Newton, which is 2000 Newton. Let's check. You can see, correct. Now, the beam shown below is balanced at its midpoint. The weight of the beam is 40 Newton. We have to calculate the unknown force Z and the length of the beam. To calculate the unknown force Z, Z is resting on the pivot. That shows is what? A contact force, right? Let's see. Yeah. Which is equals to 30 Newton plus 40 Newton plus 20 Newton. That's 90 Newton. For us to calculate the length of the beam, yes, the balancing of forces on the meter rule is first taken care of. The sum of anticlockwise moment must be equal to the sum of clockwise moment. If you should look at it, that is 30 newtons multiplied by 0.5 meters is equal to 20 newtons that we have multiplied by half. Let R serve as the distance associated with the clockwise moment. R has to do with the length, yes, associated with the 20 Newton force. So R is now what? 30 newtons times 0.5 divided by 20. That gives 0.75 meters. Now, we deal with the total length of the beam, which is then given as, that will be 0.5 plus what was our answer is 0.75. All in meters, that's 1.25 meters. Let's check. That's correct. Now, let's deal with the summary for the day. We have to choose the correct statement. Moment of a force is the turning effect of a mass about a point. No. Moment of a force is the turning effect of a mass about a field. Not correct. Moment of a force is the turning effect of a force about a point. Yes, that is what we can also call torque. So that is correct. Yeah. Now, another drill for us to get a correct statement. When an object is in equilibrium, the sum of turning forces is equal to the clockwise and anti-clockwise moment. Can that be true? When an object is in equilibrium, the total clockwise moment is not equal to the total anti-clockwise moment. That is false. When an object is in equilibrium, the total clockwise moment is equal to the total anti-clockwise moment. Correct. So let's see here. So with this, we've come to the end of today's class. Do well to join us on our website www.edubbey.com. Subscribe, and subscribe. We wish to see you, and also go to our interactive books and work on the internet. Do have a great time. Thank you.